We present CurveCloudNet, processing point clouds with 1D structure. In this work, we address the task of 3D perception, where the 3D measurements are obtained from a set of lasers traversing across the scene. This laser scanning setup is a common choice of hardware, and is particularly used in LiDAR scanners. We are interested in a method that can be flexibly applied to the various domains that use 3D laser scanners, including but not limited to high-quality scanning of individual objects, scanning large outdoor terrain, and autonomous driving. Our core research question in this work is, can we incorporate 1D laser traversals as a prior for more flexible 3D perception of laser scan scenes? We show that we can improve 3D perception by using a curve cloud. That is, point cloud backbones operate on the full scanning resolution and employ arbitrary 3D neural operations. However, they struggle to scale to larger scenes. On the other hand, sparse voxel backbones are highly scalable, but incur discretization error and are limited to axis-aligned operations. In contrast to these popular approaches, curve cloud reasoning operates directly on the raw scan, is not constrained to axis-aligned operations, and is highly scalable. Concretely, when scanning, a laser scanner traverses a laser across a scene. However, the popular point cloud representation discards the scanning information. In contrast, we use the scanning order as well as edge distances to construct a set of polylines, thereby establishing 1D local neighborhoods and maintaining the original traversal information. We develop a novel point cloud processing scheme. Given a point cloud with scanning time steps and scanned laser beam identifiers, we first parameterize the point cloud as a collection of polylines, which we denote as a curve cloud. Then, we can perform efficient and cache local operations along each curve. We make use of 3 novel curve operations: 1D farthest point sampling, curve grouping, and curve convolutions. First, farthest point sampling is often a bottleneck of existing point-based backbones, requiring k-sequential steps in order to sample k points. Instead, our 1D farthest point sampling evenly samples points along each curve and is fully parallelizable. Second, we extend PointNet++'s ball quarry grouping to operate along each curve. By constraining the groupings along curves, we can perform each neighborhood lookup in near constant time. Third and finally, we apply symmetric 1D convolutions along each polyline, treating the polyline as a 1D sequence. Importantly, this lets us leverage highly efficient convolution implementations, while still traversing the 3D space in a meaningful way. Putting everything together, we build a novel architecture named CurveCloudNet, which combines curve operations and point operations. At higher point resolutions, we employ our efficient curve operations. Then, after downsampling and arriving at a lower resolution, we employ standard point-based operations. Using point operations is important because we lose the curve structure at these lower resolutions. We evaluate CurveCloudNet on the common task of point cloud segmentation on 5 datasets that span both objects and outdoor scenes. Importantly, we are interested in an architecture that can flexibly reason in various settings. Thus, the 5 datasets significantly vary in their capture setting, scale, laser scanning pattern, number of points, and training setup. On average, CurveCloudNet outperforms a set of competitive baselines, and is either the best or second best on each dataset. Importantly, CurveCloudNet showcases high MIOU accuracy on both object part segmentation as well as semantic segmentation of large outdoor scenes. In contrast, point-based backbones struggle to scale to larger outdoor scenes, while sparse voxel backbones fail to achieve competitive accuracy in the single object setting. Qualitatively, we can observe that CurveCloudNet predicts cleaner object part segmentation on the Cortex dataset, especially in regions of the object that are more sparsely scanned. Furthermore, we can visualize CurveCloudNet's segmentation on the Audi A2D2 dataset and observe improved segmentation of the road, a truck, and a car, compared to the popular baseline Cylinder 3D. In conclusion, we present CurveCloudNet, a powerful and flexible 3D backbone designed for laser scan data, and we look forward to continuing to extend CurveCloudNet to even more 3D and laser scan domains. Thank you for listening.